Okay, so let's see how the coding is gonna go. Last time we implemented the unconditional sampling, which is without any observations, right? So it's really not too hard. Maybe we can generalize this function. Maybe we don't even need to write another function. What if we just magically call this sample from model, and we just give it measurements, which is either a torch tensor or none. And then if this is none, then we won't apply the measurement term. And that's it. Then we'll write the equation as it is, okay? So then we have the apply the unconditional update equation. And then all we need to do is apply conditional update equation. So now the forward process in MIMO channels is pretty easy. It's a matrix multiplication between the pilot matrix and the channel. So then we can say if measurements, if they're not none, then we can say conditional, okay, becomes the step size. It has exactly the same, well, we have to look in the paper now. Yes, this is yes, it is similar to a Kalman filter because there is a loop here and you iteratively filter. Yes, so that's a good point. Diffusion models are pretty much denoisers, and we're doing iterative denoising, but also with the data term here. Yes, it's an annealed, yeah, it's also an annealed process because we shrink the, I don't remember if this is what they do in Kalman filtering too, if they shrink the added noise power back into the process at every step, but there is also an exponential shrinkage here because this config R is raised to the power and it's a subunitary number. So yeah, this is signal processing, obviously, except it's done with also info from a deep neural network. So we need to apply the conditional update equation. So we have the same step size, and now I have to look in the paper because I don't really remember what it is. Okay, so here it is, same step size. So I take the current estimate, I matrix multiply with P. So I need also the pilot matrix if I have the measurement, I forgot. And then I multiply with the transpose and complex conjugate P. And I divide. I also need to know information about the noise power that is added in the measurement process. Because in wireless channels, you not only measure with matrix. Actually, we know this. We already implemented this in the first episode. But this is the forward process, right? It's pretty easy. You just take the matrix H, multiply it with a P, and you add noise with a certain power. So then I need to know the P. The Y are the measurements. I have them. I need to also know the P. I also need to know the N. And yes, we are using annealing here too. Because we're decreasing the step size. And sigma, I also need to take into account the noise that I add in the process. Okay. Let's see, can we memorize this? H times P minus Y, and okay, I think we can. And I need to flip the sign here because I want to descend in this direction. Metropolis, that's something for, I think that's a randomly, that's something to do with randomly choosing to add noise or not, right? Here we determine it, we add it every step, and also we stop after a fixed number of steps. So it's actually it's probably simpler than that. Like the stopping criterion is fixed here. We just run this process for a number of steps. Okay, so I need to know P also, so let's go back here. So then we also need pilots, which is also, we either have it or not. and we need measurement noise standard deviation, which is either a float or we don't have it. So if we have the measurements, this will be negative because we want to take a step in the, well, no, let's leave it positive. We'll update it. And then our current will be current minus conditional. Well, actually, let's do it this way. Step size times conditional. Let's compute the conditional term purely by itself. So what did we say it is? It's torch matmol. I take my current. I multiply with the pilots. I subtract the measurements. And I multiply the whole thing with the complex conjugate pilots. Dot conj dot, I need to do I have dot Hermitian in PyTorch? That would be nice. Oh, PyTorch doesn't have complex Hermitian? Not even in the last version I'm on? PyTorch complex Hermitian or it doesn't have the H? T, does T work for, so T works on complexes, does it also conjugate, or I have to do .t.conj? Also, I need this to work on, okay, so let's just mess around with it, it's probably faster. Because this is also in the batch operation. So if I have, so let's say I have X, torch, rand, n, 4, 4, 6, D type, torch, complex 64. If I do .t, what does this do? X.t.shape. It's not good because it flips everything, right? No, I just need to flip the last two. I believe it's X.transpose -1 -2. Yeah, so I need to permute the last two axes and also do conj. Because there is a difference between, yeah, okay, so there is, I'm surprised there's no there's no Hermitian. Interesting. I thought they would have it by now. But in any case, we know it's the last two axes. So what do we say we do? Pilot dot transpose dot -1 -2 dot conj. Okay, so we multiplied this. Where's the matmol? Here. Matmol. Oh, this, comma, okay. And I have to divide by measurement noise. Is it deviation or power? I think it's power. I think these are all squared. All right, squared plus, let me clean this up a bit because it looks ugly, sorry. Oh, actually, I cannot clean this up. Okay, never mind. So it's times measurement. Is it? I think it's got to be powers, right? Yeah, it's squared. Okay. So then I also take the current noise standard deviation and I square that too. Okay. So then let me see if this cleans up. Okay, it does clean up. Okay, there we go. So matmol H times P minus Y times P Hermitian divided by squared measurement noise plus noise standard deviation. And yeah, you're right. So we can do a safety check here. If not, pilots and measurement noise raise runtime error. Pilots and measurement noise must be passed together with measurements. Okay, so we know that we don't do division by nonce. And that's it. So this is directly the gradient term, right? So actually we can maybe separate this again. So let's see. Reconstructed measurements will be, well, it's just torch math mole then, okay? And then the gradient is just the difference then. Difference multiplied by the pilots divided. Okay, this is as clean as we'll probably get it. And that's it. We take a step. We want to decrease this. And then the rest remains the same. This output is given by the model. It pushes the signal to a more likely direction, but in pure, like just natural signal space. Okay, so then we're done here. So let's go back to training now. So let's also, so before we used to sample from the model, unconditional. Let's also sample conditional now, right? So we can say sample. Oh wait, we have to, what did we change here? Oh, it's just called sample from model, okay. We have to do something with these. Plot the samples, and we also sample conditional. Now to sample conditional, we need to generate the measurements in the first place, and the pilots. So now we can do this here. Yes, it is. Yep, it is likelihood. Except the likelihood comes from a deep neural network because it's not for image. It's for wireless channels, which are like they sort of look. They're still 2D signals, but they're complex valued. So they look like an environment, and the axes are receiver and transmitter number of antennas. Exactly. So the diffusion model just learns the natural distribution, and then the conditional term pushes it to be consistent with the measurements. But it is very close to image deblurring or whatever, because like wireless channel estimation is basically image estimation. So that is true. So then, okay, so first we need to generate pilots. So now, if I remember correctly, the pilots in wireless channels are pretty basic. They are just 1 over square root of 2 random plus minus 1 real and imaginary part. Let's see, how do we code this? I can take sine of torch rand like. I think this is the closest one, right? So, but for this I need a parameter that tells me the number of pilots. So actually we need another config here. Oh my god, okay, we have way too many configs, but it's better to keep them separated. So I need a measurement config. And let's use an undersampling factor, because we always want to test this when we have fewer pilots than receive antennas, because otherwise it's too easy of a problem, because you would have more measurements than the real signal. Which that's also technically an inverse problem, but it's like a much easier one. So what do we need here? Let's call it an undersampling, which is a float, and we'll put it to 0.5, half by default. I think that's it. That's all we need, because we know the pilots are always plus minus 1. So then it's just a matter of picking the right. Okay, this is not worth a config then. Hang on, where do we put this? In data? Yes, it should live in data. So undersampling, float. Okay, because we know the image size, the channel matrix size is 1664, but we're only going to observe 8 times 64 because we undersampled the. No, sorry, 16 times 32, because we do right multiply, right? So then the pilot matrix in this case will be 6432. And then when we multiply with 1664, it gives us a 1632 measurement. And our job is to estimate the channel, which is higher dimensional, from this. Okay, so this controls the... so then we need the pilot matrix to be number of transmitters times this factor. Yeah. Okay, so then we have CFG, what is it called? Data CFG dot undersampling. Okay, so then we can just look at, we don't need this now. So first we need to generate the pilot matrix, which will be 6432. So, it's a rand n. I'm just gonna take its sign though. This is the cheap way to do it. Plus another rand n with a sign. Yeah, but so the left dimension of this is always the second dimension of the image, because that multiply has to work. Now hang on, we have to do this per batch too. Why don't I do this actually? Why don't we do it the cheap way? So I'm just gonna build a full matrix. No, it doesn't work. Hang on. Okay, so the batch will be the same, okay? The other dimension is the last one, and the third dimension is the last one times the coefficient. Except we need to take an integer here, we need to round it. So CFG data dot, what do we call this? Undersampling. Except I also need to do an int here. Because I don't know if it rounds. I don't think it works there. What if the dimension is odd sized? Because I need integers. It's better to use the fixed number when we know we have it, and then just only multiply down, not up. Okay, so then it'll be, because I know this is always 0, this is always -1, and then the third dimension of the pilot is the one that changes, and it's -1 times data undersampling, and it's the same for the imaginary part. Okay, and I think that's it. Now this does look pretty ugly, so let's split this into two then. Pilot's real is just this, and pilot's imaginary is also exactly just this, and then pilots is just, I don't even need all this, it's just 1 over torch square root of 2 times pilot's real plus 1j times pilot's imaginary. Now I also do take the sign here because I only care about plus -1. Okay, this looks a bit cleaner now. Okay, so we have the pilots, then we can generate the measurements. Now it's trivial, right? It's just torch, matmul, val samples, pilots, done. Plus the noise, forgot about the noise. So we also need in data measurement noise, which is also a float, and let's put it to something small, standard deviation convention. Okay, so then we're going to do plus data config times config data dot measurement noise times torch rand n like. This is another case where I need to split. So clean measurements, I'm first gonna get these, and then the noise is just, the measurements are just measurement clean plus torch rand n like clean. Okay, and we're gonna call these noisy measurements. And I'm gonna call these clean y because the names are too long and I kind of don't like it. Okay, there we go. This is pretty clean now. So now I have all the three things I need because I have the okay, so then I can just run conditional sampling, which is exactly this. Now there is a lot of trickery here. I made a mistake because neural networks, they work with complex values, with real values. They don't work with complex values. So actually in unconditional sampling, I can stay in real world, but here I cannot. I have to be careful because this current is real valued. So what I actually have to do is I have to convert this back to complex, but I have a utility for it. So from MIMO dot data import complex to real and real to complex. So when we do this matrix multiply, I have to go back to complex world. Let's keep the pilots in complex world because it's easier. Complex world. We'll keep the measurements in complex world too. Complex world, complex. Real world. So I need to go complex to real here. Okay. And this should be it. Okay, so now I can go back. So now to sample, I need the last three arguments, which are in order, measurements, noisy, pilots, and the standard deviation of the added noise power. Okay, let's do and that's it. Let's see if this runs, and if it does run, we can do the plots. And well, it's not gonna work because we have to train a model, so the plots will look bad in the beginning, but then we can actually track this loss now during training too. So then I just uv run -m mimo.train. We probably missed a few things, but they should be easy to clean up now. Oh, I need to put defaults here. So let's do equals none, so we don't specify them. So it doesn't, so by default these are off. Okay. Okay, it's going. Okay, so first it's doing the unconditional sampling because it's gonna go through two progress bars. Now, of course, the model is not trained, so these will look badly. And maybe it's not a good idea. We're waiting too long here. I should have just commented that out, but it's fine. The interesting thing is I wonder if we can get both of them for free. I think we can, because I can just... well... No, we can't, because it's two different trajectories. What am I talking about? No. Yeah, it's not going to work. So I do have to pay twice the compute if I want to sample conditional and unconditional. Okay, that's pretty much it. So then we have 4 samples. I can just plot them in a 2x2 grid. That should be pretty basic. While this is running, now I want to see it move through the... I hope I didn't make any shape errors here. Let's see. Of course I did. Oh, yeah. Okay, so it's yelling about tensors. I hate this from PyTorch because... oh yeah, I forgot, I have to do shapes. No, what am I doing here? Sorry, it's all shapes. All right, so this is a big mistake. It's not a matrix. Okay, and let me comment this part out then, so we don't have to wait for it. And try again. Because now it'll go straight to the thing. Now I think I'm gonna get tens. Init, I can use init here independently because it's only for shapes. Yes, I can. Oh, but wait, I need validation data. I actually need real validation data. Okay, I'm just gonna do it on init. which is just random Gaussian channels, just to see if the thing works. But that has to be a real channel, so I actually need a fully sampled channel for, sorry. Which we have, because I have the validation data. It's just a matter of only get input must position 1. Also, I can't even do torch. What? I can't even do torch square root of 2? Is this how bad PyTorch is these days? Like, really? Yeah, I guess I can't. Well, this is pretty annoying. Interesting. Then it's cheaper for me to work with NumPy actually, because this works in PyTorch, multiplying a tensor. Also, I forgot to put device here, which will bite me. So device on device. Okay. Device on device. I need to import NumPy. Yeah, no, it's easier with the thing is now you get to the problem with multiplying a number with a tensor, but interestingly enough, that one does work in PyTorch, right? If I do 3.1 times torch randan 1, yeah, this does work. Okay, so at least, okay, so now I have tensor. This is scalar, tensor, scalar, but it's fine because it's multiplied. Randan like takes care of the device. Are the pilots on the right device? They are. Is the init on the right device? It is. Okay, this function should work. Okay, we're much closer now. Okay, so now we have we sample the pilots. The only thing we can do to be a bit cheeky is we can say early stop, early exit. We can early exit on the external loop, on the outer loop. Early exit if we encounter NaN, because there's no point anymore. Yeah, we shouldn't continue. So if I think torch has is NaN, so if current dot is, really, it has it, right? Yes, it does. Is NaN dot any. If we see even one NaN, we can just return current. We're gonna have to print a warning though. Which reminds me, we have to also use proper logging, which we don't do because we want to log this at warning level. Warning, sampling exited early because of NaN values. Interestingly, PyTorch doesn't crash. It lets you put the NaN through a deep neural network, but it's like you're literally wasting compute. So we can do it at it's okay. These inner steps are, it's just one, so I don't even have them. But then once we hit something, we can early exit, and that's it. This is for conditional sampling. Okay, so next time we can load the validation data, or yeah. So this was it for conditional sampling.